Okay, so this is a course on stereology and quantitative microscopy, and I'm going to introduce to you in this first lecture actually what is stereology. So, if you the term itself, if you look at it, goes back now more than 50 years back, and why did it evolve? Why did we require such a technique that we will be discussing, or in characterizing microstructures? And here the characterization of microstructure implies we are talking about geometrical characterization, such as volume fraction of a second phase. It can be size of particles, size distribution of particles. It could be size or size distribution of grains. It could be density of dislocations. So, many different quantifications that are geometrically possible with microstructures, and we do know that the microstructures evolve as a result of the processing you do to the material, and that in turn governs the properties of the materials, and that is why there is a requirement for characterization of these structures. For example, volume fraction is going to affect perhaps the strength property, the ductility. Grain size, for example, can again impact mechanical properties and so on. So, the term stereology dates back to the 1960s, and what stereology attempts to do, it's to relate two-dimensional images. See, when you look at a microstructure, it is a two-dimensional image. The structure we have is actually three-dimensional. So, how do I relate a two-dimensional image to the three-dimensional structure? For example, volume fraction is a three-dimensional quantity, but you are only looking at a two-dimensional image. Even size of a particle is a three-dimensional quantity, but you are again looking at a two-dimensional image. And this brings in some challenges as to how you can relate what you observe and measure on a two-dimensional microstructure to what parameter in the three-dimensional microstructure. So, again, quantification of geometrical features of the structure is what stereology is about, and in order to do it, it consists of many mathematical tools which enable you to transform two-dimensional measurements you measure on a plane microstructure to three-dimensional parameter of the structure. And some of the three-dimensional parameters, as I said, could be volume fraction, size distribution, and so on. So, before we proceed into the geometrical characterization, let us look at what are the geometrical elements which make up a microstructure. I can isolate those elements. For example, if you look at a block of material in which what are the constituents? Constituents could be linear elements like dislocations, like triple edges. It could be surfaces like grain boundary surfaces, or it could be solid particles. Okay. So, I have these various features: 3D particles, 2D surfaces or interfaces, and one-dimensional linear features such as dislocations, grain edges, fibers in a composite material. Now, what do I do in order to, but our material is opaque. Generally, most of the materials that we as material scientists deal with are opaque materials. So, we can't see it. So, in order to observe these the structure in the material, what do? I actually take a section through the material. That is the simplest way of doing it. Polish it and put it under some microscope. It could be an optical microscope or a scanning electron microscope, and observe the structure. And I have to, of course, prepare the surface. So, I polish the surface and then etch it and so on. Here is what we are actually doing. That one is taking this section through the three-dimensional block, and on that section I observe it under some microscope. So, what will I see? If there are linear or line features, you will get them as points on the section, isn't it? If a section cuts a line, you will get a point. If a section cuts a boundary, a surface, you will get a line. And if a section cuts a 3-dimensional solid particle, you will get a section of that particle, which would be a 2-dimensional profile. This is one way of observing a microstructure like this. Another way we observe microstructure, if you think back, is producing a projected image, which is possible if my material was transparent to light. If this material was transparent to light, then I will get lines will be projected as lines, surfaces will be projected as area elements, and solid particles will also be projected as area elements, forming a projected image. For biologists to understand this, is very straightforward, because they use a transmitted light microscopy, because their tissues or that they are observing are generally transparent to light. So, they are able to get a projected image. Even as material scientists, when we used a transmission electron microscope, we project the structure onto a 2-dimensional plane. So, these are two different ways of observing the structure. One is a section image and other is a projected image. And you can clearly see that these two images are very different. What you would observe as points on a section image, you would get lines on a projected image. Both of these structures, both of these 2-dimensional images can be quantified and then related to the 3-dimensional structure, but the stereology behind them can be quite different as to how to do this transformation. So, in these set of lectures, we would deal only with the planar section. We will not be dealing with the stereology of projected images in these set of lectures. So, just to summarize, basic elements of interest are 3-dimensional objects, surfaces of 3-dimensional objects, or interfaces or boundaries of grains, of 1-dimensional linear elements, grain edges, dislocations, fibers, etc. Now, let us have a look at some real microstructures and the tools that we use to observe these microstructures. I am sure that most of you would be aware of the optical microscope, whether it is a reflected light microscope, which is what we call as the metallurgical microscope for opaque materials, and then you have the transmitted light microscope, where the light goes through the sample, which means the sample has to be transparent to light. Going to electron microscopes, you have scanning electron microscopes, where you can get secondary or backscattered electron images, even X-ray map images, or going to transmission electron microscope, which becomes again a projected image then, if you are using transmission electron microscopy. Then you have plethora of other microscopy tools, such as the atomic force microscope, scanning, tunneling microscope, etc. All of these will give me 2-dimensional images. Here is some examples. This is what you would observe in a typical nodular cast iron, put under a reflected light microscope or a metallurgical microscope. This is a single phase polycrystalline material, where you can see the grains, and you see these black lines, which are the grain boundaries, which in the 3-dimensional structure are actually surfaces. So, what you see here, for example, these lines meeting at one point, and this typically you will see that grains are meeting at one point, 3 grains are meeting at one point, or 3 grain boundaries are meeting at one point, which we call as the triple point. In the 3-dimensional structure, this triple point is actually a line, which would be a triple edge, where 3 grain boundary planes are meeting, forming a linear element. So, if I look at these two microstructures, what I am seeing? I am seeing section profiles of the graphite nodules, which are actually 3-dimensional solid objects inside the material. In this polycrystal image, I am seeing lines, which are actually surfaces. I am seeing these triple points, which are actually lines Okay. So, these are the, so you are able to isolate the various geometrical elements of a structure. Here is a microstructure observed in a scanning electron microscope of a ferrite perlite structure of a plain carbon steel. So, here actually the perlite colonies are shown prominently, where you have alternate lamellae of ferrite and cementite. Now, one of the things that one is interested in, which also control the property of steel, is how fine these lamellae are. What is the interlamellar spacing? Now, we will see that stereology can be used to quantify such a parameter like the what is called as a true interlamellar spacing. The interlamellar spacing that you see on a two-dimensional image is not the true spacing. The true spacing is the perpendicular distance between the planes of ferrite and cementite that are existing. What you are seeing are only a section profile of these planes, and depending on what angle the section cuts, the spacing will be different on a two-dimensional image. So, how can I convert a measurement where the spacing is not the true spacing to actually to the true spacing? So, we will see how stereology will help us to do that. This is simply a more magnified image of a perlite using a atomic force microscope. Here is a couple of projected images now in a transmission electron microscope. So, here you are seeing basically again this is a single phase polycrystalline material, in which this top image you see 3 distinct grains and 3 grain boundary planes meeting at a triple edge. Okay. So, this is a projected image where you can make out where the triple edge is, and the image below shows linear elements which are projected. And what are these linear elements? These linear elements are the dislocations in the material. So, projection is preserving the line as line in the image. So, now we come to a important concept of stereology, which is sectioning of a material. Okay. Generally sectioning, we can cut section a 3-dimensional block with a 2-dimensional plane, or we can also section using a line, or we can section using a point. Now, what does this mean? All of this sectioning processes are also termed as sampling of the material, and sampling by probes of various dimensions. If I take a 2-dimensional section, the probe is 2-dimensional. If I section it with a line, the probe is 1-dimensional. If I section it with a point, the probe is 0-dimensional. Now, to understand this, sampling by a 2-dimensional probe or a plane probe is essentially nothing but intersection of a plane with the 3-dimensional structure. So, when I intersect a 3-dimensional structure with a plane, then I see that lines will appear where surfaces were there, points will appear where line elements were there in the 3-dimensional structure, and area elements or section profiles will appear where particles were present in the material. So, this is called sampling by a 2-dimensional probe. Now, what is sampling by a 1-dimensional probe or a line? Well, on this 2-dimensional probe, if I put, for example, these grid of lines, these horizontal and vertical lines, then this is sampling the structure by these lines. These lines then are called as simply a line probe, and if you take any one particular line, for example, if you take this line, then one can look at the intersection that the line makes with the features, with the geometrical features of the structure. Okay. So, for example, this line intersects this particle. I can look at this intersection by maybe intersection with the boundary of the particle, or I can look at it as a line intersection with the solid particle itself, and then I can look at the length that this line makes within the particle. I can look at the intersection of the line with these what you are seeing as line is actually surfaces in 3 dimensions. So, I can look at the line intersection with the surface. Okay. So, this is called sampling by a line probe. Then finally, sampling by a 0 dimensional probe or the point probe. The point probe, if I look at the intersection of these horizontal and vertical lines, they intersect at a point. So, I can consider these intersection as points, and these are all the point probes. Okay. This is a point probe, this is a point probe, and this is a point probe, this is a point probe. Now, again, just like with a plane probe and a line probe, I can look at intersection of these points with the structure. For example, I am only interested in looking at how many points are going to intersect the particles. So, this is one intersection with the particle, this is another intersection with the particle, this is another intersection with the particle. Okay. So, I am use these probes in order to understand the structure. We will see this as the stereology unfolds, that what exactly are we meaning when we are sampling with these probes. But one thing to realize is this sampling word is used in a statistical concept, which I will be coming later. So, let us continue with this interaction of the probes with the structure. Okay. So, if my 3 dimensional feature here in this column, if it is a volume feature like a solid particle, and if there is a plane probe, if this plane probe intersects this 3 dimensional feature, then there is an event that is produced, and the event could be the cross section area, okay, or simply the cross section. And the measurement we can make of that event is the area. This is one possible measurement one can make. Okay. There are other measurements, of course, I can also measure the perimeter for that matter. If it is a surface feature and the plane probe, and we are using a plane probe, then the event is a line trace. Okay. And one of the measurements that we can make is the length of the sectioned line. If you take a line feature in the 3 dimensional probe cutting with a plane probe, you would get a point intersection, right. A line with a plane will get a point intersection. How many such points are there? You can count them. So, how many such events are there? You can count them. Similarly, volume feature again, and line probe is used, you would get a intercept length, the length within the line probe passing through the 3 dimensional feature, and the length and the intercepted length within the volume feature, and you can make a length measurement. Similarly, a surface feature intersecting with the line probe, you will get a point intersection, and such points can be counted. Volume feature with a point probe, you would get a point intersection, and again all such points can be counted. So, these are the various combination of these probes. One probe that I did not mention, because if you look at all of these probes, we have looked at 2 dimensional probe, 1 dimensional probe, 0 dimensional probe. All of these probes have a dimension which is lower than the dimension of the microstructure. This is a key point to note. There is one more probe which is actually a volume probe, which is called the dissector, We will briefly look at that particular probe later on in this set of lectures. And this word event that I am using, this is coming again from a concept of probability, that when we would be talking about what is called as geometrical probability, that if an event occurs, there is a certain probability of that event. So, for example, if a two-dimensional probe, a plane probe intersects a particle, there is a probability of intersection of that plane probe with that particle. What is that probability? We will have a look at that, because all the stereology is then built up on such concepts like the geometrical probability. Because if there are let us say large number of particles and there is a plane probe which cuts the structure, not all the particles will be cut, only some of them will be cut. How many of them will be cut would depend on what is the probability of the plane probe intersecting the particles. So, important consequences. One, as I said, probe is of a lower dimension than the structure, and a consequence of that is that it leads to loss of information. For example, suppose I see on a microstructure elliptical shapes. What is the shape of such particles in the three-dimensional structure? I can't be very sure. It could be coming from ellipsoidal particles, but it could also come from cylindrical particles. That would also produce many such ellipses. So, because the probe is of a lower dimension, the information that we lose is shape. So, many times in order to analyze, we have to assume certain shapes in order to go further with the analysis. Since probability is strongly linked with the stereological methods, stereological methods are going to be of statistical in nature. And just like when you collect data, statistical data, one obtains average values, and these average values are subjected to random or statistical errors. And we will take couple of examples where we will see that how we can deal with these errors, how we can compute these errors or random errors that are there, or the statistical errors that are there. And third, stereological methods have mathematical rigor. Okay? So, they are based on a very strong footing of probability and statistics, as we will see in this. Okay. Before I even try to explore these the foundations of stereology, let us take straight away an example of the method of stereology. The three structures that you are seeing, these are actually hypothetical structures, but they may be coming from spherical particles in 3 dimensions, and they have been sectioned by plane probes. So, you will get circular profiles of varying diameters. Okay. Now, suppose I wanted to find, even if I forget about what the 3-dimensional structure is, suppose in this I wanted to find what is the area fraction of these particles, that is, what is the total area of a particle in a unit area of the image. Okay. Of course, one can do this directly also, that simply since these are circular particles, I can simply measure the diameter and then of each particle, and then I calculate what is the total area occupied by these particles. That area divided by the total area of the image in which these particles are distributed would give me the area fraction. But if we are dealing with very large number of particles, which we have to in order to get a good estimate, because your microstructures are going to vary from place to place in a statistical manner. So, just one small region will not give you a very accurate estimate. So, I have to take several areas, and hence it may be very tedious if I have to do this manually, okay. And then there are going to be also my manual errors that I will make and so on. Of course, I can do this with automated image analysis, but not all microstructures we can use automated analysis as well. So, for time being, let us just consider just these two-dimensional images, and I have to calculate what is the area fraction from all of these three structures and take an average value. So, I will present a stereological method to do this, which should be very fast and which we would be doing, you will be doing in this class shortly yourself. Put a grid of points on these images. Now, these grid of points are again the intersections of the horizontal and the vertical lines. I see I could have put isolated points, but those points are difficult to see, and that is why we put a grid of points, so that this is a point, this is a point, this is a point, this is a point, and so on. So, if you look at this, there are total of 64 points in each grid, okay. So, and then the event that I am looking at. So, this is a point probe that I have applied, and the event is, out of those 64 points, how many points are falling inside the circular particles, okay. So, for example, this is a point here. So, this is a point that falls inside the circular particle. This is another point which falls inside the circular particle. This is a third point that falls inside the third circular particles. And I calculate what is called as a point fraction. Small n here represents the number of points that intersect the particles. So, small n represents those kind of events, divided by the total number of points I have in the grid, in this case 64 points. Now, I get a point fraction value from each of the three microstructures, and I calculate an average value of point fraction, which I have represented in triangular brackets to represent the average. And this average point fraction is an estimate, direct estimate of the area fraction. So, this is a stereological method which would give me an estimate of the area fraction, as again with statistical or random error associated with it, which we will see also to calculate that random error. Now, this particular microstructure set of is the same particles, but now I am focusing on the boundary of the particles, okay, the interfaces of the particles. Okay, so, this is the phase boundary between the particle and the matrix, and I again put a grid, but this time I remove the vertical lines. I will just keep the horizontal lines, okay, and I count the number of intersections these horizontal lines make with the boundary. So, for instance, this is a intersection, this is another intersection, this is another intersection, and so on. So, you count this intersection, you count this intersection as well, you count this one, this one, this one, this one, a total of all the intersections that are there. I have just highlighted only 3 of them, and then let that be small n in a particular image. In this image I will get some small n number of intersections. I divide that by the total length of these horizontal lines. Okay. So, I measure the length of one of the horizontal lines and then add up the lengths of all of them put together. This is what we call as the number of intersections per unit length, and the symbol that I am using is P sub L. Okay. Using this, get an average PL from all the 3 images in this case, and then I present another relationship whose foundations are based in stereology, that the average diameter of these particles in the 2-dimensional image is the ratio of point fraction that we had calculated in the previous slide divided by the number of intersections per unit length PL, which calculated here. This ratio multiplied by a factor of 8 upon pi gives me the average diameter of the particles. Okay. So, these are 2 relationships I presented, and what we can do next is actually perform this analysis on a real microstructure. Okay. So, I will close this lecture here, and we can look in the next lecture where these relationships are applied.